All right, let's dive in. Today, we're going to talk about something incredible, an invisible force that powers pretty much our entire world. We're talking everything from giant industrial machines all the way down to the quietest thoughts inside your own head. It's this hidden partnership between two of nature's biggest forces, and it all starts with a question. So think about it. You've got a simple compass, right? The motor spinning inside a fan, and then the crazy technology that lets us see inside our own brains. I mean, what in the world could these things possibly have in common? Well, it turns out they all run on the exact same incredibly powerful principle. And that hidden connection, it's called electromagnetism. It's the wild idea that electricity and magnetism aren't really two different things, but actually two sides of the same incredible coin. And the craziest part, the story of how we figured this all out, well, it started completely by accident. Okay, so let's jump in our time machine. We're heading back to the 19th century, where one scientist's little moment of curiosity during a totally normal lecture, well, it would go on to change the entire world. So picture this. It's 1820. A guy named Hans Christian Ørsted is in the middle of a lecture. He's got a basic electrical circuit set up, and just kind of sitting nearby on the table is a compass. Well, when he switches on the power, he just happens to notice the compass needle twitch. It just moves, pointing away from north. It was this tiny, totally unexpected little flicker, but it was the very first proof of a deep, powerful connection. And you gotta understand, this was a huge deal. Before Ørsted, everyone thought electricity and magnetism were completely separate things. His simple little observation that an electric current could actually move a magnet smashed those two ideas together. It created a brand new field of science and opened the door for basically every piece of modern tech we use today. Okay, so to really get what Ørsted stumbled upon, we need to try and visualize what's actually happening around a magnet. We need to, see the invisible. So, every single magnet is surrounded by what we call a magnetic field. Think of it like a magnet's personal bubble, its zone of influence. It's this area around it where its force can actually be felt. And that force isn't just random. It has both a strength, or magnitude, and a very specific direction. So how in the world do you see something that's invisible? Well, there's a classic experiment for that. You just take a magnet, put some paper over it, and sprinkle some tiny iron filings on top. Give the paper a little tap, and poof, the filings just snap into place. They form this beautiful, almost magical pattern. They are literally tracing the invisible lines of that force field. And what you're seeing here, it's not random at all. It's actually showing us the rules of the game for magnetic fields. These lines always flow out of the North Pole and loop around back into the South Pole. And you can see where the lines are all bunched up close together. That's where the field is the strongest. And here's a big one. These lines will never cross each other. Ever. Okay, so that's a regular magnet. But remember Ørsted and his wire? What about electricity? How does it make its own version of a magnetic field? Well, this is what was messing with Ørsted's compass. Anytime you have electricity flowing through a wire, it's not just a boring old wire anymore. It's suddenly surrounded by its very own magnetic field. And unlike the field from a bar magnet, this one is shaped like a series of perfect, concentric circles. Okay, circles, cool. But which way are they spinning? Clockwise, counterclockwise? How do we figure out the direction of this invisible force? Well, lucky for us, there's a super easy trick for this. It's called the right-hand thumb rule. Just imagine grabbing the wire with your right hand and point your thumb in the same direction the current is flowing. The way your fingers naturally curl around the wire, that's the exact direction of the magnetic field. Pretty cool, right? Now, what happens if we take that one wire and we coil it up over and over again into a tight spring shape? That's called a solenoid. When you do that, something amazing happens. All those little circular fields from each loop of wire, they all add up. They join forces to create one big, strong, and really uniform magnetic field right down the middle. And it looks almost exactly like the fields from a regular bar magnet. And this is the absolute game changer. A normal bar magnet is, well, it's always on. You can't switch it off, and you can't really change how strong it is. But an electromagnet? You can turn it on and off with a flick of a switch. You can make it way stronger or way weaker just by changing the current. And that right there, that control, is everything. It's what makes electromagnets so unbelievably useful. All right, so let's flip this whole thing on its head. We know a current can create a magnetic field. But what happens if you take a wire that's already carrying a current and you stick it inside another magnetic field? Turns out the field pushes back. A magnet will actually exert a real physical force on a wire with current flowing through it, and that force makes the wire move. And that simple push, that is the secret sauce behind every single electric motor on the planet, from the one in your electric toothbrush to the massive ones that power trains. So, same question as before, right? Which way is it going to move? Up, down, left, right? How can we predict the direction of this push? You guessed it, there's a hand rule for this too. But this time we use our left hand. It's called Fleming's left hand rule. You can do this right now. Hold up your left hand and point your fingers so they're all at right angles to each other. Your forefinger points in the direction of the magnetic field. Your middle finger points in the direction of the current. And your thumb will show you the direction of the thrust or the force. And once you know about this interaction, you start seeing it absolutely everywhere. It's not just in motors. It's how loudspeakers vibrate to create sound. It's how microphones work in reverse to capture sound. It's even the key principle behind electric generators and tons of other scientific instruments. Okay, for this last part, we're going to bring this whole idea somewhere you might not expect, inside our own bodies, where it plays a really surprising and, frankly, life-saving role. So what's with this wild number? Well, your body is electric. Your nerve cells talk to each other using tiny little electrical signals. These signals are basically just a flow of charged ions, and that flow of charge, that's a current, so it creates its own magnetic field. But they are unbelievably tiny. We're talking 1/billionth the strength of the Earth's magnetic field, just ridiculously small. But here's the thing. When millions or even billions of these cells fire all at once, like in your heart or your brain, those tiny little fields add up to something we can actually measure. And we've built a technology called MRI, magnetic resonance imaging, that can detect these incredibly faint fields. It allows doctors to create stunningly detailed pictures of our organs and tissues, all without making a single cut. And that's how we circle back to the very beginning. That's how we get those incredible images of your brain. So we've seen how electricity can make a magnetic field, and we've seen how a magnetic field can push on electricity to create motion, which leads us to one last, really big question. If we can turn electricity into magnetism, can we do the reverse? Can a magnetic field be used to create an electric current out of thin air? Well, that's a story for another time. Thanks for tuning in.